Great to see you all on a Friday afternoon towards the end of the conference, when you could be out in London enjoying the beautiful weather. Hi, everyone. I'm with Bernie here, and I'm Ganesh, and we are going to be talking about infra-level transparent checkpointing for resilient AI/ML workloads. Believe it or not, that is me without a beard, and I am a software engineer in the Azure Kubernetes Service team at Microsoft. At AKS, we run a managed Kubernetes service platform, which allows you to run a variety of compute workloads, including lots of ML training and inference workloads. And we have users running these workloads at extremely large scales. I particularly work on GPU provisioning and making it easier to run a variety of GPU workloads on the platform. I've also previously worked on speeding up pod start time through a feature called artifact streaming.
Yeah, my name is Bernie Wu. I'm the VP of Technology Partnerships for a company called MemVerge. MemVerge is a Silicon Valley-based startup that has software that we've developed that helps on memory virtualization and also checkpointing software. And so we're hoping to bring those two kinds of capabilities into the AI/ML area. On a personal note, I live part-time in Hawaii, and I noticed that the culture of the Kubernetes community in Hawaii is very similar. There's a very friendly culture, one that helps each other, and it's almost like an extended family, or what we call ohana in Hawaii. And we also, in Hawaii, we like to welcome new people. That's called the aloha spirit. So one of these days, I hope we'll have KubeCon over in Hawaii. Anyway, back to you.
Thank you. In today's talk, we'll start off with a brief poll, then talk about the motivation for why we want to do this approach and what are the other current approaches that people are taking to address these problems. Then we'll define what infra-level transparent checkpointing is, talk about use cases and limitations, and then Bernie will share about how it works and show some cool demos to see this in action. And we'll also talk about some open areas that we could address together as a community. For this part, I would really, really love your participation. There'll be 3 questions. First one, how many of you have run GPU workloads in Kubernetes? Please raise your hands. Wow, that's great. Almost everyone here has done that, as expected. And then, how many of you are not satisfied with the existing solutions for resilience? Things like handling GPU failures or node downtime. Could you please raise your hands? OK, almost all of you who raised previously too. And how many of you care about resilience more for training or fine-tuning? OK, that's about half of you. And what about for inference? All right, there's a good number, but fewer than for training. That's sort of the mix that I've heard from conversations with folks too. And then finally, how many of you are focused on improving the utilization of your GPU infrastructure? OK, awesome, awesome. Great. Almost all of you raised your hands, which is good to know, because GPUs are expensive, and you could probably save a few, several $1,000s of money by improving the infrastructure utilization. And this is also validated by many papers and reports that have come out. You probably have seen the Llama 3 paper with how frequent GPU errors are, and the different types of issues that that people are encountering, especially for training. And then we've seen talks in this conference as well, talking about the frequency of GPU errors. There's also surveys which validate what you're experiencing around low GPU utilization. So about a third of users have less than or equal to 30% of GPU usage, according to this survey. But how do we address these challenges today, and how can we make it better? Today, many users are running GPU health checks that are integrated as part of node problem detector. And those can be also combined with a remedy controller, which can take actions like rebooting the node or resetting the GPU. This helps you in identifying issues and taking mitigation steps. But it still has questions on how you can handle the application efficiently. Because you face issues around things like scheduling dead time and also slow pod starts, because when you have a new node that needs to be provisioned, that takes a while, and if you have a large model that takes several GBs or sometimes multiple 100 GBs is going to take a long time to load. We talked about some aspects from the infra provider perspective and also from a user perspective in this KubeCon Salt Lake City talk. But now we're going to address the other side of how we make it easier from the application perspective such that they don't have to think about these problems on their own. Another approach that's commonly done is model checkpointing during training. It's done frequently, and then if a node goes down, you just restore from the registry or another repository where you have the previous checkpoints of the model weight stored, and then you can continue the training process. Some approaches include basically interrupting your workload as well, and that's a naive approach, and then just migrating to a new node if there's issues. You could also use tools like Q and Volcano to make this process easier, along with some GPU sharing strategies like multi-instance GPUs. But all of these address different aspects of the problem. They still face some common challenges like slow loading time and recovery time for your end-to-end workload. You might need to configure your applications as well to handle things like recovery from the last checkpoint. It could also lead to higher costs, and we think that this could be made more resilient. So what is infra-level transparent checkpointing? This is the aspect that we want to talk about today, and we want to define it in phrase by phrase. So checkpoint here represents capturing the entire state of the running application with the point-in-time memory and all the associated files so that you can basically pause, migrate, and hot restart it later. Transparent refers to the application code or frameworks not needing to be changed. So the application does not need to be aware of this checkpointing process. Then infra-level refers to this completely being handled by orchestrators or schedulers and the platform itself so that users don't need to worry about it. I want to really emphasize this point that this is not model checkpointing. It's not just model checkpointing because you're capturing the entire application state in your container. And from the usage perspective, it's the people at the platform layer who would really care about the solution from the implementation aspect. And this is, as you know, an emerging topic, and we are in the emerging track too, so not everything is going to be fitting perfectly, but so we'll have open discussions at the end. So if you're new to this, you might have many questions. How production ready is it? Can you restore it on different GPUs? What type of different machines can you restore it on? How do you handle network state? How much time does it take to do all these additional computations? And we'll be addressing some of these questions, but I would also highly recommend multiple other talks that you could look at for more details. So for a high-level overview, think of yourself as a neural network that is running on a double-decker bus in London, taking the views of the city, learning about it, and updating your neural network weights. Unfortunately, your bus breaks down, so your application container cannot start running. You cannot continue training. What happens next? Well, without you knowing it, almost a snapshot of you from 2 minutes ago was taken and kept in the British Museum. Now, we want to be able to restore that and continue running it. So this is the checkpointing phase, and that was kept in the museum. And then now you spin up a new node where you can continue running your application. But instead of going through some application-specific logic, you can recover to where you were from just 2 minutes ago and continue as if nothing happened, pretty much. So you're going to be almost like the severed people in the show Severance, or unlike them, you're going to remember what you did. So all the training, the neural network weights that you updated are still going to be there, and you can continue running it. So because we've captured the entire memory state, that will also be restored in this process. And this will help in improving resilience, and we'll also talk about how it improves utilization. So there's a host of challenges that this can address. So there's 3 categories. One, which we call scheduling optimization, another for handling node downtime, and then the third one for pod start time improvements. For scheduling, if you have a higher priority workload that comes in, or if you have idle resources that are scheduled but actually not being utilized, or if you have spot instances that can go away anytime, you could use this checkpoint restore approach to be able to migrate your workloads, or you could also use it to handle it efficiently. And then, especially when you have long-running jobs that need to be taken over by another job, we need to have a seamless process for capturing the state and being able to save it somewhere and then restore it. So this helps there. And then for node downtime, like the original chart that I showed with GPU issues, you can add to that end-to-end flow to be able to checkpoint right before the GPU goes down, or if you're draining the node, and then restore it when you go to a new node. And a lot of these use cases are unlocked by the faster time it takes to load the new container image and the application. And many companies are starting to already use this for speeding up their pod start times. So what are the other ML-specific use cases that we may be able to address with this? For inference, many of you might assume that inference can be considered as a stateless application, but is it really stateless? Well, according to one definition, stateful applications save past and present information, while stateless applications don't. For inference, let's say for LLMs, you tend to store values like the key value cache values in memory, and that could be both in GPU memory and in CPU memory. And if you lose the inference workload and the KV cache is only present on your node, then that memory would have to be recomputed later with most current approaches. But with transparent checkpointing, it might be possible to restore that state and continue running your application without much need for additional recomputation. But one requirement there is the time to reload the KV cache must be less than the time needed to recompute it. Then for distributed ML training, in this time chart, you see checkpoints being done at a regular cadence. This is from a Microsoft research paper, this graph, and they were talking about how to optimize checkpointing from the model layer. So the model, I need to mention that the model checkpointing will still happen even with infra-level checkpointing, because model-level checkpointing is useful for experimentation and if you want to go back to a previous state. So we will be complementing this model-level checkpointing with infra-level checkpointing. So we take perhaps more frequent checkpoints and then restore it if there is an issue in between 2 model checkpoints. So in this time chart, you see that if there's a failure in between checkpoint 3 and checkpoint 4, you'd have to retrain from checkpoint 3. That wastes additional cycles, basically, for GPU and CPU. But also because when you have a distributed training case, many other nodes in your entire cluster will also have to wait for your one node to be restored and then the progress to be synced. Because at the end of each checkpoint, typically, they will be syncing their gradients and the weights. But this is not a solution to everything. There are some limitations that we need to be aware of and address. One being that the checkpointing at the infra layer is not aware of the application state itself, which means that the checkpoint could be significantly larger compared to just app-level checkpointing. So let's say for inference, for the model itself will take up most of the space, but you also have additional libraries and helper functions that will be loaded onto memory that would also be copied over. And depending on the application, the amount of memory the difference between the 2 checkpoints can be significant as well. Then there's rigid requirements for restoration sometimes, where you might have to match the machine configurations, but also this varies on the type of checkpointing implementation you use. And then you'd want to have restore in a machine which obviously has the same or higher memory. There's also some resource considerations, like how much compute time it takes, and that can vary between periodic and event-driven checkpointing. So these are pretty much two types of checkpointing you can do. So periodic is like the word, you keep checkpointing every few minutes or a few seconds based on how you configure it. And then event-driven is if you know that there's going to be a failure, then you can checkpoint it, and then keep the latest checkpoint. This graph there is sort of a high-level graph on the trade-offs that are involved in figuring out what type of checkpointing we want to do. So on the y-axis, you see the total cost of operating a workload, and then on the x, you see the checkpoint frequency. So if your checkpoint frequency is really low, you're going to checkpoint after a very long period of time. The additional compute overhead for checkpointing is going to be low, but your resilience to errors and recovery time will be high because you might need to recompute it if you error out. And then on the other extreme, if you're checkpointing really frequently, your compute consumption is going to be significantly higher, but your overall resilience might be better, but the total cost of operating your job would be higher as well. So we need to find a sweet spot for how frequently you need to checkpoint, and that will vary also depending on the type of application and also the type of GPUs that you have, the error rate, and other factors. Bernie will continue, and he'll share about how it works and show some cool demos.
OK, great. Thanks, Ganesh. Yeah, so as Ganesh discussed, he's now defined what infra-level transparent checkpointing is. He's described some use cases that we see are possibilities. And he's also described the limitations of checkpointing. And so now what I want to do is just deep dive a little bit more into how we're trying to implement transparent checkpointing for Kubernetes. And everything is centered around an open source project called CRI-O. CRI-O stands for Checkpoint, Restore, and Userspace. CRI-O was started in 2012. It's designed to checkpoint applications running on Linux platforms. And it's in wide production with other virtual machine platforms for doing live migrations. And then my company, MemVerge, has been using CRI-O as part of a spot instance migration of long-running HPC batch workloads on public clouds. In addition to that, CRI-O is incorporated, if you don't know already, into Kubernetes. The 130 release supports forensic examination of containers. So those containers are checkpointed by CRI-O. And in addition to that, in KubeCon Paris last year, I gave a brief talk on some work that we done with NVIDIA to introduce GPU-level checkpointing to this community. And so I demonstrated an operator that could do a GPU-CPU checkpoint of a single workload running on a pod and successfully restarted elsewhere. There's ongoing work by the community and they've created a very nice GPU plugin for CRI-O that also will support the AMD GPU. And I want to give a shout out to, excuse me, Radisson and Adrian here in the front row, and their colleague Victoria. They presented yesterday, and so if you want to read more about the history of CRI-O and where the CRI-O project actually stands, those are the folks to talk to. In addition to all that work, what we did was we have to make this ready for production level workloads. As Ganesh referred to, we need to do something about the checkpoint overhead. And so in that U-shaped curve we showed in the previous slide, what we're trying to do is lower that curve and flatten it out so we get a very highly efficient checkpointing technology. And to do that, from our experience working with HPC batch workloads, we are focused primarily on reducing the checkpoint interruption time, production interruption time, and then also the space consumption by the checkpoints, and then also computer and memory resources that are being used to execute these checkpoints. And so we've been successful with HPC workloads doing that using a combination of what we call asynchronous checkpointing, compression technologies, and then also even incremental checkpointing. And in the case of asynchronous types of checkpointing, we've been able to reduce the window, the checkpoint production interruption window from anywhere between 30 and 100x, 100 times better than just running it without any kind of asynchronicity. And then with compression, we've been able to achieve up to 5-to-1 levels of compression and incremental snapshots also for situations where we have very, very narrow times to handle preemption signals. So we're hoping to bring all those kinds of capabilities to bear on the Kubernetes problem, and so part of that is we also have a lot of experience working with external events like spot instance preemption signals, working with schedulers. So we've done integrations already with, on the HPC side, with Slurm, LSF, and HTC Condor. And we're hoping to bring that kind of know-how to bear also. So we just started working with Q and the JobSet projects to integrate there. Another consideration for operationalizing this kind of checkpointing is security issues. As you guys know, as you may know, the CRI-O actually has to run in a privileged state because it needs to checkpoint all the different pods within that particular node. So there's some security things we have to address there. And then also, sometimes there's third-party license managers that need to be taken care of when they're checkpointed and things are being moved around. And then ephemeral files is another area. I think right now you're allowed to spill memory onto a disk, and you're also allowed to have ephemeral files as part of your workloads. And so those also need to be checkpointed and moved elsewhere if you're going to do a hot restart somewhere else. And then lastly, we're continuing to work with NVIDIA to improve the checkpointing features in terms of fractional GPUs and things like that, and then also improve the overall performance and flexibility to be checkpointed and migrate to different types of environments. So those are all ongoing efforts to operationalize checkpointing here. And just to give you a quick idea of what's going on, right now the GPU checkpointing is currently a 2-stage process. The first stage is to checkpoint, to actually halt further job submissions to the GPU, and this is done on a process ID basis, halt submissions. And then secondly, wait for that particular process to complete, and then we take that memory, dump it to system memory. So that's the first stage, and then from system memory, we're also checkpointing the system memory plus the GPU memory that's just been dumped there, along with any kinds of ephemeral files and things like that, taking that all and dumping that onto a persistent volume somewhere, or some sort of directory. And the restoration process is simply the reverse of that, a 2-stage process currently. Now, last year, again, I showed a single node being checkpointed and hot restarted. We wanted to extend that to a distributed architecture. So the key components of that are, first of all, there's a high-level coordinator. This coordinator's role is to, first of all, discover membership of who belongs in this particular distributed cluster. And we do that by mapping out the network relationships between all the workers and doing a self-discovery. But in addition to that, we've also have an option to just basically query the JobSet API and just find out where are the workers. And then that's one component. Another component is the synchronizer. Synchronizer's job, as you can see on the right side of this thing, is to make sure all the workers, when they're invoking this CRI-O operation, are all doing it concurrently. So there's this place where in the CRI-O design where you can put an action script hook called at the pre-dump stage to make sure that all the checkpoints are occurring simultaneously, and then conversely on the other side of the checkpoint, there's a post-dump barrier there where we can make sure everything is also released simultaneously. And the purpose of that is to make sure there's no messages in transit and things like that that could be lost or corrupted by having things checkpointed out of sync. And then we also have a webhook that allows us to provide for particular applications a checkpoint path or to a persistent volume or whatever, so that we know where this checkpoint is being stored. And there's a daemon set to deploy this on each host. And we do use a modified version of runC. And the goal of that is to Runc would normally pull off the a cold restart container off of the registry, but in this case, Runc will then go to a directory path if there is one for a checkpoint and bring the image in that way. So that's the basics of how our cluster transparent checkpointing is excuse me, implemented. And then to automate all this, naturally we got to put this in an operator. And the goal of this operator is to create a graceful preemption and hot restart of a workload, whether it's an individual node application or a distributed one. And so we look at this as a way to reduce what we call the friction of moving or hibernating stateful long-running workloads. And a lot of AI, ML workloads have that kind of characteristic. And so this is basically there's two ways we can implement this thing. One is to implement it as a sidecar, or we can also implement this, deploy this via daemon set. So for the purposes of using this for node maintenance, we're implementing, implementing this as a daemon set deployment. And pretty much off-the-shelf components that are listed there. The only thing that's been modified, off-the-shelf CRI-O version 4, for example, the only thing that's been modified is the runc so that we can direct it to a checkpoint path to pull the checkpointed image. This is what we're talking about, the kind of a use case that we're working on. It's called JobSet migration. The first type of migration is for a scheduler to use to take a set of pods in a particular distributed cluster and move them in an entirety to some other location. This could be used to help maybe defragment a particular infrastructure and also to use it for prioritizing higher priority jobs to take over the resources, et cetera. And then the second one is more for node maintenance. What I discovered during this conference, which was really interesting, is that it seems like almost 90% of these failures that you see with GPUs can actually be corrected by just simply evacuating the node and rebooting it. So we see this scenario where we're actually dealing with, again, that distributed cluster, but we're just moving one node, the failing node or the one that has the problem, over to a hot spare and then maybe rebooting the hot spare. So I think there's also been a lot of progress in doing predictive kinds of work on predicting which nodes may be failing, and so this kind of technique I think would help in node maintenance. So just before I go into this, the demo itself, I just want to explain what we're trying to do here. To keep things simple, we have just three nodes in this, 3 workers in each demo. The first demo is going to be a bare metal demo of a 2-node PyTorch distributed cluster, and we're going to use our periodic checkpoint. So when you see that to checkpoint and fail, we'll manually walk through that demo, so you'll be able to see every step of this process. And then what we'll do is we'll fail over to a spare node, and then you'll be able to see it resume operation. Now, because it's periodic, you'll see it roll back to the epoch where it actually, in this case, was checkpointed. So when we do the checkpoint, it continues running, but when we do the restoration, it will roll back to the last checkpoint. The second demo is we're going to show more automated things, so that's going to happen a lot faster. So you got to be alert. But that's a job set migration, so that's more of an event-driven thing. The event will be we're typing in there to take this node out of maintenance. We'll automatically take that node out of maintenance, migrate the workload to the spare, and resume operation. That's all done with Q and the job sets. So let me now switch over to the demos. Okay. So this is the first demo. It's the bare metal demo. Okay, it's running good. So there's two workers there, a master and a worker, and they're already running this PyTorch distributed thing. So you can see the epochs and batches going. They're scrolling by, and also we're running the GPUs. So we're pulling up the SMI, NVIDIA SMI tool to verify the GPUs are up and running. That's on the bottom there. Then also I want to show you that we're showing you the TCP/IP connection, so these things are chatting a lot with each other. And so that's what's being highlighted there in the bottom windows there in the demo. Again, this is going to be a manual demonstration. Then we pulled up in the middle there, this is our checkpoint coordinator, our synchronizer, that will make sure that these two nodes, when they're checkpointed below, are aligned with each other. And so we're typing in a manual checkpoint for each one. And so they're both being checkpointed and coordinated. And the checkpointing, you can start seeing on the lower left, the checkpoint dump files. Now on the lower right, the dump files is being checkpointed. Now, if you notice above, the application is continuing to run, so the checkpoint occurred fairly quickly, and it was about at epoch 5 when the checkpoint occurred, but everything is still progressing. And so now what we're doing is we're trying to rsync the lower right worker to a spare node, which we haven't shown yet because it's not, I haven't posted it yet on the screen there, but we're doing an rsync and just copying the files manually. And so you can see all the files listed there on that lower right side of the window. So it's taking a little while to rsync it. And then what we're doing is we're going to kill that worker and then switch the monitor on the upper right so that we can see the spare node. So that's being set up right now. And again, this is the manual demo, so I just wanted you to see this. And while this thing is running, I also want to give a shout out to my colleagues, Ron and Vincent, back in California that did all the hard work of putting these demos together. And then, so now the checkpoint coordinator has been invoked again to do the restoration process, and all the files are being reloaded, and the system is being restarted. And pretty soon you'll start seeing the checkpoint log. It's the distributed PyTorch log scrolling along again. So there it goes. It's resuming, and it actually resumed. Even though the job continued running, we actually ended up rolling it back to about epoch 5 in this demo. So that's the manual demo of a checkpoint and a hot restart with a rollback to the last periodic checkpoint. And now, I would like to show you the the automated version of this. So here, what we have is we're going to demonstrate taking a node out of maintenance using an operator. So we have 3 nodes set up and then a master. And we're using Q, the Q project, to migrate from node 3 to node 1. And then also, we're showing this job set notion. So the job set is called PyTorch Distributed Training. That's what we just highlighted there. That's the job set. And then what we're doing here is we're going to show the log so you can watch the epochs and batches go by. And so we'll show you later on that there's total continuity even though we restarted it elsewhere. Now we're highlighting node 3 because that's the one we're going to take down. This is a maintenance CRD that we set up in conjunction with our operator. Then we also set up a maintenance shell script, and all you have to do is basically execute the maintenance shell script and just put the node name in, and then everything's automated after that. And that's what we're doing right now. We're invoking the maintenance shell script. If you look immediately above in that kind of panel, you'll see that you'll see a quick termination and a start of the containers above it and the other nodes. So there's the termination. There's the new creation of the new replacement container. And then, let's see, where are we here? Okay, now we're starting up this log thing again. You can see it pretty much resumed where it left off. It'll scroll up some more, so you'll be able to see that. While we're waiting for it to scroll up, you'll also be able to see this checkpoint file. That's where we right now we're just dumping these into an NFS file, but just to show you where these checkpoints are, we're just showing you that in the upper right corner there. So anyway, there you go. And if you look at this bottom corner, bottom right corner, you'll be able to see that we resumed right where we left off, basically on epoch 9 batch 1000 there. So that's the demo. I hope you Enjoyed that. And let me make some concluding remarks here. Sorry. Yeah, so next steps and call to action. So what I just showed you today is that we demonstrated the feasibility of using an operator to transparently checkpoint and hot restart a distributed PyTorch AI/ML workload and improve its resiliency. And so our next steps will be to continue to, this is kind of a crawl, walk, run, but we're going to work on overhead optimization, characterization, how to scale this up. We believe it should be highly scalable because everything can be done parallel on each node, the checkpointing process. And then also we have a lot of work to do on back-end networks. We'll probably start with the RDMA kinds of connectivity, and then also telemetry and integration with Prometheus. And then we also want to continue to work with the CUDA and the CRI-O communities to improve functionality and capabilities and contribute back there. And then my call to action for you folks is we appreciate any feedback, evaluation, or specific use cases. If you want to give this an early try, that would be great. Evaluation. And we are very interested in working with the scheduler community and orchestrators and even application frameworks. We see possibilities of where this could be used in that context to help with checkpointing or to coordinate checkpointing, and then also spot instances. And we want to keep ramping this up and validating things at scale. So with that, I'd like to thank you very much and have Ganesh come back up here. I see, do we have any time left? Oops. Okay. Did we overshoot?
Yeah, we are a bit over. Thank you.
I apologize. Thank you.
I think we'll take questions in the hallway later, and then we'll also upload the slide deck for reference and with additional references to previous talks too. Thank you.
Thank you.